Today, we want to get into looking at partial derivatives, how to find them and what we can use them for. The good news is that we already know this. This is the same derivative stuff that we learned way back in Calc 1. We already have mechanics and we already have thinking. We just need to modify the mechanics and the thinking to fit functions of two variables and then move that beyond. So we've already got mechanics, we've already got how we think about derivatives. We just need to modify it to cover surfaces and so on. So if you would recall, when we had derivatives in Calc 1, we were trying to find the slope of a line tangent to a curve at a given point. We wanted to find the slope of a line tangent to a curve at a given point. So if we had some curve, we described that curve with a function, and then we had some point. And then we had some tangent line. And the thing that we know is that the slope of that line is the derivative of the function evaluated at the point. So the slope is f prime evaluated at c. The equation of the tangent line, we have a point and a slope, so we can describe the equation of the tangent line. So the point that over here would be c comma f of c. So our location is c f of c. Now that we have a point and a slope, we can write the equation of the line. So the equation of the line so there's the equation of the line tangent to the curve at the given point. In R2, a linear function in two variables will describe a line. That was a little bit redundant. In R2, a linear equation will describe a line. In R2, a linear equation is a line. In R2, a linear equation describes a line. All this is the same if we go up to a function of two variables. We're going to use the same kind of thinking. Instead of a curve, we have a surface. Instead of a tangent line, we have a tangent plane. The at a given point part, that's the same. So instead of a curve, we'll have a surface. We're going to find the equation we're just going to update what we had before. Instead of finding the slope of a line tangent to a curve at a given point, we're going to find the slopes, two of them, of the plane tangent to a surface at a given point. We're doing the same thing. We'll have some surface. I'm going to draw it from the side. We're going to pick a point on the surface since it's described as a function. I'll just label this point x naught, y naught. And z is the height above that point. At that point on the surface, I've got a tangent plane. Where before we had a tangent line. Now we have a surface and a tangent plane. We're looking at it from the side, so I don't have to draw things in 3/4 view. And a tangent plane has two different slopes, has two slopes. So there are going to be two slopes. They're going to be defined by derivatives. There's two of them, so we're going to need two derivatives. And then we can use those slopes to describe the plane tangent to the surface at a point. So here, before y equals f of x is our curve. Now z equals f of xy is our surface. And we know what the equation of a plane should look like. I'm going to use the same form we used over here. Z is our function evaluated at x naught, y naught, our point. Oops. Looks like a subscript. We're going to describe this in the same way. Our function will start at, our plane will start at a point, and I'll just use this location here. So this point here is the point x naught, y naught, f at x naught, y naught. The function evaluated at the point. And so just like with the equation of a line, we'll start our equation of the plane with a location. There will be a slope in the x direction and a slope in the y direction. Two slopes, m and n. M is telling us how z is changing in the x direction. So m is the change in z divided by the change in x, and n is the change in z divided by the change in y. Whereas in the case of a line, we only had one slope, the change in y divided by the change in x. Scroll down. In R3, a linear equation describes a plane. So everything matches up. We are doing the same thing. We are approximating our curve with a line, or we are approximating our surface with a plane. We are approximating our function with a linear function. We're approximating our funky function with a linear function near a point. This only applies, this is a local thing. When you look close enough, everything is flat. If you move to a different location, it will look differently flat. We are approximating our function with a linear equation. We are approximating a function with a linear equation. Whether we're using a line to approximate a curve or a plane to approximate a surface locally. So we're creating a local approximation. The same thing that we've always done with this derivative business. Is everybody okay? So we're going to do the same thing mechanically that we did before. We're thinking of these derivatives in terms of slope. This is why we want to come back to this tangent plane business with the two slopes, and also why we wanted to write those two slopes as dz dx and dz dy, because it compares favorably to the way we wrote the equation of a line, where f prime of c was dy dx, sorry, delta y over delta x. The delta y over delta x just becomes dy over dx, when instead of having some positive delta x, we let delta x get small, go to 0. What we're really looking at here with the slope, or one of the things that we could think about looking at here with the slope, is we're trying to calculate a slope. Slope requires 2 points, change in y divided by change in x. But if we try to do that with 1 point, we get 0 over 0 over 0. 0 over 0 is different than something like 1 divided by 0. 1 divided by 0 is undefined. It cannot be anything. 0 divided by 0 is not undefined. 0 divided by 0 is a different kind of undefined called indeterminate. 0 divided by 0 is different, because sometimes 0 divided by 0 is 0. Sometimes 0 divided by 0 is some constant. And sometimes 0 divided by 0 is positive infinity or negative infinity. Think about the slope of the tangent line. Sometimes the tangent line is flat. We're calculating the slope, getting 0 over 0, but since the function is flat at the point, we say 0 divided by 0 is 0. Sometimes the slope is some positive number, like the slope of the tangent line to x squared when x is equal to 3. There, the slope is 6. In that case, we're finding the slope, delta y over delta x, 0 divided by 0, and coming up with 6. So 1 divided by 0, undefined, no question about it. 0 divided by 0, what do you want it to be? We have some notation, because this is math, and we love notation. So we have for derivatives f prime of x, our Newton style notation, and dy over dx, our Leibniz style notation. If we want to evaluate these at a point, we would just say f prime at c I wrote x naught, I meant c, or dy dx evaluated at x naught. Our prime notation is really good for functions, showing that we're plugging something in. Our Leibniz notation, not so good. Our Leibniz notation, really good for showing what the slope is, showing the derivative as a slope. Change in y divided by change in x, only instead of delta, we use a d because it's really tiny change in y divided by really tiny change in x. Now, in the case of partial derivatives, we're going to have two of them. There's going to be a delta z over delta x and a delta z over delta y. So we do a couple of things. Number one, we use two different, since there are two different partial derivatives, when we're doing partial derivatives, we use a different kind of d. So for partial derivatives, we'll have a delta z over delta x. When they become really small, we're going to say dz over dx. We're going to say dz over dx, but we're not going to write that. We're going to write these weird looking d. So we're going to say dz dx. That's the partial of z with respect to x. So make a backward 6. What's that? Not quite. Because a lowercase omega is kind of like a delta. Sorry, a w. So we make a backward 6. We still say dz dx. But when we look at it, it's not like a regular d, it's this curvy d, the backward 6 style. This is because notation. So we'll say dz dx, but we'll all understand that we're dealing with partial derivatives. But we have another one. We also have a dz dy, and we do the same kind of thing. Make a backward 6, dz, backward 6, dy. The reason that we like this notation is because it looks like a slope. It looks like delta z over delta x, which is what we're trying to describe. We're trying to describe the slope. We're trying to describe a direction. So how is z changing in the x direction? How is z changing in the y direction? What's that? Yeah, it's like a delta, but it's not quite a delta because the regular delta has like a, it's like the top is kind of like curved backwards. Yes. dy dx. This is just evaluate this expression at this point. So dy dx evaluated at x naught. That's what we do for Leibniz notation when we want to evaluate, plug in a point, because we don't have the parentheses available. So here, for our function style notation with the prime, we could just say evaluate f prime at x naught. So here's how we note evaluate dy dx at x naught. So prime is not specific enough. We have two different derivatives. We've got an x derivative and a y derivative. So we can't just say prime, that's no good. So what we do is we create two different notations for our prime style. So we'll say f, we make a subscript of x at x. So there's the partial derivative of f with respect to x. So instead of writing a prime, oops, I put an x. I have just an x. So for our prime notation, I can't just put a prime because there are two of them. Which prime is it? So instead, we say we'll take the derivative of f with respect to x, and then this will be a function of x and y. So we make a subscript of the variable with which we are taking the derivative, with respect to which with the bottom one. So the partial of f with respect to y is fy at xy. We make a subscript because we have two different derivatives. When we have a function of x and y, there's a derivative of f with respect to x and a derivative of f with respect to y. So we can't just say prime, that's not specific enough. We have to say the fx at xy or fy. And the way we read these is just like I just did. We say fx, then at xy, fx, and this is fy. That is shorthand notation for how we speak these. This is how they will be said in conversation. We'll say things like fx at xy, and you'll have to know that I mean the partial derivative of f with respect to x. And then you can see why we're going to just say fx. Because it's a lot to say the partial derivative of f with respect to x every single time. So here's our notation for first partial derivatives. We have our thinking in play. It's the same thinking that we had before. We have some modified notation. We have modified notation for prime and our modified slope or Leibniz style notation. Because we're only looking at part of the derivative. We're looking at how the function is changing just in the x direction. So that's not how the function is changing. It's just in one specific direction. So we're only partially looking at how things are changing. Yeah, in Calc 1, we didn't have to make that distinction because there was only one variable. That's why Calc 1 was so simple. There was only one variable. So we didn't even have to say the derivative of f with respect to x all the time, because what else is it going to be with respect to? So most of the time we just said the derivative. But now there are two of them, so we can't just say the derivative. We've got to be specific. And we call them partial derivatives because they're only describing how the function is changing in one direction, in the x direction or the y direction. This opens up the problem. What if we want a direction other than x or other than y? And that's where vectors have to come into it. Well, we got to build some more machinery first. So these are first partial derivatives. Thinking, same. Notation, modified. Mechanics. So this is just doing the thing. This is nx to the n minus 1, but for functions of two variables. So good news. You already know all the rules. Chain rule, product rule, quotient rule if you want to be fancy. All we need is chain rule and product rule, but we got chain rule, product rule, quotient rule, the basics. Should have listed that first. The basics would be things like the derivative with respect to x of x to the n. Is nx to the n minus 1. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of e to the kx is k e to the kx, derivative of natural log of x is 1 over x, derivative of tangent is secant squared, derivative of secant is secant tangent. All the ones that you know. The difference is now we're going to have functions of two variables. The idea that we're going to use is that we're going to take the derivative with respect to x. We're just going to imagine that y is constant. Treat the other one as a constant. When finding the partial with respect to x, we're going to treat y as constant. This means that y could show up as a constant term or a constant variable. Remember, we treat them differently. Constant term, constant variable. It's term or factor. Yikes. Constant variable. What the heck? So we're going to be treating y as a constant, either a constant term or a constant factor. When finding fy, We're going to treat x as constant. Either as a term or as a factor. Now it's just a matter of practice. Do thousands of problems and it'll be second nature. It's like, I don't know if you had to ask this question in Calc 1. The question comes up, how do we know which rule to apply? Eventually, you just know. That has to be it. You just have to know. Like when you're out driving, you're about to make a turn. How much do you turn the wheel? How do you know how much to turn the wheel? You don't logically know. You just know. You turn it enough so that the car does what you want. You do it fast enough so that the car does it when you want. And you just have to know. You just have to drive around a bunch of parking lots until you figure it out. And since this is the United States, all you need to do is drive around a couple of parking lots for a little while, take a test where you drive around the block, and then apparently you can drive 6,000 pounds of van anywhere on any road, and everybody's cool with it. You know what I mean? It's kind of insane. Like you could be a 16-year-old kid, get your motorcycle license, and go out and buy a 1-liter bike. That is like designed to murder you. The motorcycle is like, oh, I'm gonna kill you. And you're like a 16-year-old kid, probably a boy person, because only boys would be this stupid. But there's like, oh, I'm gonna go buy a big 1-liter bike. Michael, why? Because fast. And the bike's like, oh, I'm gonna kill you so hard. You are dead, right? Like other places, like, oh, we're gonna start you off on essentially a bicycle with a motorcycle on it, with an engine on it. And so you have to start off like on a 250cc. And so you're driving down the street, and it's like, oh, whee, you know, you just have to live with that. Once you prove that you cannot die doing that, then you can get like build up to it. You know what I mean? But in the United States, you can buy your 16-year-old kid just got their license a fucking Corvette. Because I don't know. I think parents that do that should be tried for murder when their kid wraps it around a tree. And they go, you bought your kid a Corvette. Well, yeah, I wanted him to have a nice car. And he wrapped it around a tree. Yeah, it's like, oh, murder. You're under arrest. If you didn't want the kid, just put him up for adoption. Come on, man. You know what I mean? I'm just kidding. I'm just kidding. Don't at me, Jesus. I turn off comments so no one can say shit. What's that? It's not compared to other places. Like in California, it's difficult because partially it's difficult because we don't train you. Like imagine if I gave you a calculus test like right now on partial derivatives, and this is all I've done. That's kind of what happens, and that's kind of the difficult part. Anybody watch Rally, like Group B Rally, back when Group B Rally was a thing? It's like a car racing, but instead of like on a track, it's like sometimes you're on pavement and sometimes you're on dirt. And the cars are like, you take like a Ford Fiesta or something like that and just make it have 600 horsepower and make it weigh less. And then find an absolutely crazy person to just drive it fast, like through really curvy streets, right? Like Lombard Street in San Francisco. They go, whoa, it's so crazy. Get a rally driver and they're like, well, yeah, I'm just going to have to drift around this whole thing so I could do it at 70 miles an hour or some ridiculous thing like that. Anyway, a lot of the best drivers were Finnish. Go look up on YouTube what it takes to get a driver's license in Finland. Like to get a driver's license, one of the things you have to do is lose control of the car and regain control of the car. Part of the fucking test is like, okay, it's really slippery out there. It's like 2 of your wheels are going to be on dry pavement, 2 of your wheels are going to be on wet pavement. Your car is going to go out of control. Get it back. Off you go. And here, like, I've been driving a car that's been out of control in my entire life 3 times. There are 3 times where I lost control of the car. 2 times I knew what to do because I don't even know why. Because I had lost control that one time and I didn't get it back. So the next 2 times I did. But you just gotta fucking practice this shit. Yeah, see. But and the problem is you have to practice these things. Like most of the reasons that we have for accidents are because we're not ready. We've never been in this situation before, and now we're going 60 miles per hour and our car is not in contact with the road anymore. And we don't know what to do. How could we know what to do? We've never been in that situation before. Does that make sense? That would be like me giving you a calculus test on partial derivatives right now. So put your stuff away. We're going to have a test. I'm just kidding. Yeah, and part of not following rules is that our rules don't really mean shit. Like, what's the speed limit up on 280? It's like 65. It's like 65 for like passenger cars. There are some places like on I-5 where it's up to 70. But does anybody drive 65 miles per hour on 280? Say between San Bruno and San Mateo. Does anybody do it? Does anybody get pulled over for it? How fast do you have to be going on 280 to get pulled over for speeding? It's a good question because it depends. It's different for almost everybody in this room. For me, it's a lot higher than probably the rest of you. It depends on the officer. It depends on a lot of things, right? That makes it a shitty rule. That means it's not actually a rule because it doesn't apply to me, and it would definitely apply to some of you. Right. And if it's a recommendation, it's not a rule. And if you can get punished for it, it can't just be some recommendation. You can't just leave it up to someone's judgment about what's reasonable. You can't just have a recommendation and then get punished for it. Like my recommendation is you do the homework, but you get 0 points if you don't do the homework. So that's not okay for me to say doing the homework is recommended if you don't want to lose your freedom, right? If you don't want the state to impose violence upon you. It's right, it's implied, so it's a recommendation, but it's written as a law in case they want to use it that way. Because the fact is, I can drive on 280 all day, every day at 80 miles per hour, and no one look at me sideways. They see the car that I'm driving, it's like, kind of suspicious. They pull up, it's like, oh, it's just some old math professor. They won't care. But there are some of you in this room, if you're driving down there at 70 and they don't like you, they'll just fucking pull you over. It's a law that will apply to you, but not to me. That's not a law. That's bullshit. I think that's the technical term for it, bullshit. So anyway, what are we talking about? Oh, I get mad. Speeding is bullshit. You could make it a rule. You could say, what do most people do? You could update it, say, what do most people do? Most people drive 80 miles per hour. That's like 80% of the population. If you just put them on an open road, that's how fast they'll go, depending on their car, right? And depending on how stupid they are. What's worse is the grandpa driving on the left side at 40. At a certain point, highways need to be off limits to you, right? Part of your driving test would be like, get on the highway. And if you don't go with the flow of traffic, if you don't go 80 miles, and if it's open, it's like, I'll push it up to 80. If you're like, oh, no, that's too fast. Like, okay, your license says no highway for you. I mean, do you know what I mean? Now, it seems like it's unfair, but that's because we're still thinking like Americans. We're still thinking, oh, it's just me getting from point A to point B. And that's not what driving is at all. Driving is not just you getting from point A to point B in the manner that you want. It's all of us collectively getting to our individual point A and point B. It is a team sport. Driving on public roads is not an individual event. It is a team event. We're all trying to do it. Does that make sense? It's cooperation, and we have to fucking cooperate because we're barely trained to operate our machines and they could all kill us, right? One person being a deviant could kill us all, not at once. That would be pretty impressive, actually. It's like all of a sudden a whole city died because one person was driving like an asshole. But it's a collective thing. You know what I mean? That's why when you tint your windows, I don't care until I can't see your face anymore. Then fuck you. Because we need to communicate. And if we can't see your face through your side window when you're the driver, we can't communicate. It happens all the time. I'll be like out walking my dog or something like that, and someone will pull up with a tinted driver's side window, and I will just stop. And they'll be waving me on to go. And you know what? I'm not going to fucking go because I can't see them waving me on. I don't know that they know that I'm here because they've tinted their fucking windows to whatever it is, like 5% or whatever. You look cool. It makes you an asshole because you're not communicating. And it's one of the things you have to do when you're driving, because it's not just you getting around. It's all of us getting around. Does that make sense? My point is, we are all doing this together. Anyway. It's kind of annoying because to get to this building, you essentially have to cross 3 streets. I know it's like 3 streets that are in a parking lot, and you kind of expect people to be reasonable in a parking lot, but they aren't. Because they're like, oh, I'm late for class. And so they speed through the fucking parking lot. When you do that, fuck you. Just be late. Just be late because you put us all in danger. And I do have a say with how you operate your vehicle, because your bad operation puts the rest of us in danger. It's so simple. We're in this together. Don't be an asshole. That being said, I needed only 5 minutes to do the next example because you already know how to do this shit. Check it out. Let's suppose that f of xy is x cubed y to the 5th. Function of 2 variables. What's the partial of f with respect to x? I was also doing the dirty trick, waiting for you all pack up. It's like, nah, one more example. And you're like, oh, fuck you, leech. What would you guess is the partial with respect to x? So y to the 5th, treat that as constant. 3x squared, y to the 5th. Because y to the 5th is constant, right? We treat the other one as constant. We're looking at how things are changing in the x direction. So we're ignoring how things are changing in the y direction. What's partial with respect to y? X cubed, and then times 5y to the 4th. We treat x cubed as constant. In this case, the x cubed is a constant factor, just like y to the 5th was a constant factor. Constant factors get pulled along. Told you, y'all knew how to do this already. Let's change things up. See, I knew you were gonna try to get away with 1 page of notes. Oh, haha, I've had to go to a second page, so y'all have to go to a second page. One suffers, all suffer, collective. If we have g of x is x cubed plus y to the 5th, remember, partial with respect to x treating y as constant. What's the derivative with respect to x? Anything else? Anything else? Why not anything else? Y to the 5th is a constant, and this time it's a constant term. It's included through addition, makes it a constant term, and the derivative of a constant is equal to 0. Nice. See, I told you, you guys already know how to do this. We could have had that test today. You'd have gotten all A's. I'm like, oh shit, we could just cancel the rest of class. Give you all A's right now. What's the derivative with respect to y? 5y to the 4th. We already know the reason. all we have to do is make sure that we're reading constants as constant terms or constant factors, because that's the only time the word constant matters when we're taking derivatives. Now we just need to pair this with product rule, quotient rule, chain rule, and we'll be experts in a few thousand problems. And you'll never miss anything ever again. Except for those times that you do. Because, I mean, I still get shit wrong. Question. We can't do prime because we have two different ones. Is that prime for an X or a prime for a Y? So that's why we have. And it look, I guess we decided it looked weird to have X as a superscript. So we made them subscripts. What's that? Well, we had to modify Newton's notation, but Newton's notation was trash in the beginning. Originally, Newton was like, oh yeah, we'll take the F and put a dot over it. It's like, well, you can't type that, Newton. You can only write that. Like, well, yes, well, I'm writing it all the time. You figure out how to print it. And then they were like, oh, you know what? Screw you, Newton. So, anyway, well, that's going to do it for today. Tomorrow we'll do more derivative stuff. We didn't have 5x to the third. I have x to the third times 5y to the fourth, and then I just rearranged it so it looked right. So here, we're saying the x cubed is constant, derivative of y to the fifth is 5y to the fourth. And then we're like, oh, I hate this constant in the middle. So we write it to make it look like a proper monomial. All right, that's it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing. You too.